when I'm saying polygeneration, is combination of heat pumps and cogeneration systems, mainly in buildings. So why is it needed? Well, it's mainly needed when you have on the same grid consumers and producers that can be defaced by the fact that they can profit from inertia, okay, in the system. And this is typically what is happening with microgrids. When you have microgrids, in fact, you have the equivalent of virtual power plants that are producing or consuming electricity, but they are all interacting together first, and then interacting with the major grid. And virtual power plants can be prosumers, so they can consume and produce. Typically heat-driven, so it's cogeneration and heat pumps. And I will make then a short remark when you have photovoltaics that are added to the system. And as you have heat storage tanks, then it makes sense to be predictive in the control in such a way that you are able to fill the tanks, knowing that you will empty the tanks later on. So it's not just a question of collecting the heat, but it's also collecting the heat with the goal of, by knowing that you are going to use the heat later on. And in fact, I have to look at these systems in a really integrated way. So it means that here the node can be a building, but it's a building perhaps together with cars. If I have a plug-in vehicle, for example, and this node is not only connected to the electrical grid, but it's also connected to the gas grid, and can be considered as a small node of a very bigger node. If I'm looking at the operation of such a system over one day, so this is a 24-hour operation of a building in which you have the heating requirements in blue, the electricity consumption in red, and the photovoltaic production in green. So what you can see here is that you have different operating conditions that do not necessarily occur at the same time. Okay, so it means that I could have used the multi-period approach that I have shown before, except that now I know that what I'm going to do during this period will have an influence on the next one, because I have the possibility of perhaps operating now the cogeneration unit to a higher level here, just to avoid having to operate in the next hours. So physically, this is the system that you are going to look at. So we have a building that has a comfort requirement. So it means that I want to be heated when I'm home, not when I'm at the office. No? I need light. I need the air quality as well. The building has a certain mass, a certain inertia. The reason why we are not, you are cold today is mainly because the system is not well regulated today. Okay? They have to tune it. Right? And it's mainly because we do not understand the mass. Because as soon as you increase the temperature here, okay, you have to heat the walls as well, and this stores energy. In addition to this, on the roof you can have solar panels, you can have PV, and everything will be then related to storage tanks for the domestic water, for the heating, that will be fed by heat pumps or cogeneration units in this case, that will be operated according to the price that is given by the electrical grid, perhaps by the fact that I have electricity stored in batteries, and perhaps by the fact that I have to try to use the production of PV when the sun is shining. Which means that I need this smart box that is going to realize the optimal operation of the system. And what I'm going to discuss now is how we can design this kind of boxes, knowing that on the one hand, I need to have this tool that is making the organization between the different users, the storage tanks, and the operation of the energy conversion units. But knowing as well that I have to size those equipments, so the size of the tanks, the size of the battery, the size of the heat pump and the cogeneration unit, the size of the solar panels, so that I will make a maximum of profit. So or I will pay less for my my services that I need. Okay, so I have to make the whole design of the system. So what does it mean? It means that on the one hand, I have to consider the needs. So I have to know what is the comfort requirement. So when do I have at home and when do I need which temperature? I have to consider at the same time the electricity consumption and the services. Okay, so I have, for example, a dishwasher. I have a laundry system that can be also considered as being loads that can be managed. So, for example, I can decide that when I put my dish in the dishwasher, I can say, okay, I would like to have it finished at a certain time, and let the controller to decide when it will start the washing cycle. Okay, if he knows when the electricity, when the PV panels will be fed by lights, then they will perhaps decide to start at the right time, but not perhaps at the same time as the heat pump, because the heat pump is also consuming the same electricity. Then. It means that I need predictions. I have to predict what will be the consumptions, which are related to what is happening outside. So I have to have a prediction of the light. I have to have a prediction of what will be the temperature of the buildings, and I have also to have an information about what will be the energy market, because they will give me a price to operate or not. And I have to know how I'm going to work with my system, considering that on the one hand I have to take into account the tanks levels, and then in the other hand I have to consider the way each unit will be operated. So when do I start which unit and how much does it cost to start? Okay. Doing the design means that I will have to look not only at the investment of the units in the system, but also looking at the operating costs that I will have in the system, which depends on the cost of electricity, that depends on the time, which depends on the cost of the resources, that depends on the time. And something which is important here, you can see that this problem is expressed not as a single building, but as a combination of buildings. So I would like to know at the end, if I have 10 buildings, how many buildings will receive a heat pump, how many buildings will be receiving a cogeneration unit, for example, and what will be the amount of PV panels that I will put on the roof, and what will be the volumes of the hot water tanks and of the heat distribution tank. Okay. I will have constraints that will perhaps limit the power of the electricity that I can get from the grid. Okay. Or that would limit the variations. So I cannot go and make ping pong between consuming and not consuming. So I'm limited by the scale of the variation. And of course, I have to supply the energy services. And then I'm going to write constraints. So constraints are going to tell me, okay, what is the electricity balance? What is the heat production by my cogeneration unit, for example, or by the heat pump? What is the storage balance? And the storage is an accumulation in the tank, okay, which is fed at a certain temperature, by the heating system, and that is going to lose some. So there is a storage loss that is calculated here. That is going to lose energy due to the fact that it is at a certain temperature, and that by the heat transfer there will be some losses. Okay, which then will push me to produce the heat the closer as possible of the time I'm going to use it, but at the same time with the smaller possible price. Okay, and in addition to this, then I will add so it's the heat. So what are the predictions that I need? I need to know what are the ambient conditions. I need also to know how the people do behave. I will not make the same design if I'm living the whole day at home, or if I know that I will go to the office every day. It will not necessarily be the same design. It has to be. It will be multi-nodes. I have several buildings that can interact via the subgrids. A priori, they are interacting via the electrical grid, but we can also connect buildings together with the heating, with district heating. And they will afterwards, inside the node, interact, and then outside they will interact with the main grids. And this introduces the concept of the virtual power plant. I will skip this one just to tell you the way we have done it. So again, it's a B-level optimization strategy in which, on the one hand, we are going to define what are the best configurations. So we choose the size of the gas turbine, the size of the cogeneration unit, the size of the heat pump, the size of the storage tanks. Once we have this, then we are going to do an optimal control based on some typical days. And the typical days are selected in such a way that they will represent the load curve over the year with a minimum number of typical days. And the idea is to avoid to have a lot of computations to be done. And it makes sense to do it like this because most of the time the people forget that the equipments, and the reason why we are doing these calculations is for assessing the operating cost over a 20-year time slot of a 20-year time of operation. Okay, with unknown climate conditions. Okay, so typically we look in the past and we take a typical year that we multiply by 20 times, but we could also say, okay, let's just consider that the typical year can be divided into 7 days. In this case, it was 7 days, in which we are going to add, one one extreme day that represents the extreme conditions that the system has to satisfy. But the advantage of doing this decomposition is that instead of calculating 220,000 steps, I can solve the problem with only 49 steps. Okay? And of course, from the resolution point of view, it makes a very big difference because we have factor 5,000 in the for the evaluation. So if I'm calculating, once I have made the calculation of what is the typical operating strategy that I will use in the system, I will obtain the flows in the system that allows me to calculate how much it costs per year and how much will be the emissions. Then afterwards, I can do an optimization. So here it's a optimization of the total cost. So on one hand, you have the total cost, and here you have the CO2 emissions. And you can see that you can have a Pareto curve with a list of solutions. And here you have the number of the amount of heat pumps that are installed in the district that I have calculated, the amount, the size of the heat pump in building 1, 2, 3, and 4 here, as well for the cogen. So you can see that there are some buildings that do not have cogen and others that have the 2 units. Okay. And you have here the backup boiler and the size of the storage in the different buildings for one of the points. So it's a solution which is here, which has been selected. Okay. What are the characteristics of the system? So we have calculated the size. We have calculated the size of the storage tanks. We have obtained the expected operating conditions. And one of the difficulties that is realized here is that it's quite easy to make a prediction of what did happen in the past to make a design. Which means that when we do the design, we just look at what was observed in the past, and then we say, okay, what is happening if I'm replacing my boiler by a very new efficient system? Okay. Now you define the size. You know that you have this nice box that has to operate, but you have to operate it now. Okay? And as soon as you start with the heat pump and the storage tanks and your nice box, then you realize that the box has a problem of predicting really what is going to happen, because now it has to predict what will be the future. The future is always difficult to predict. And not only you have at the level of the demand, so you have to take into account the way the people will behave. You have also to account for the way that your environment will evolve. You will have also stochasticity coming from the market. And you will have also to take into account the real technology. So what are the real what is the real part load efficiency of the equipment? How much time does it take to make the startup? What is the energy consumption for the startup, for the shutdown? How much time it has to wait before it can be restarted again? And how it will connect to the grid. So I'm going to look at what is happening in my system and how the management box has to be set up. So this is the picture of the management box, in which you have on the one hand an interface with the sensors. So you have sensors here and here that is giving you an information about the state and the state of the environment. Knowing this history here, you are able to make some predictions that is going to tell us, okay, what is expected to happen in the future, that you will then mix with the actual state definition, that you will compare with the previous states as well in order to make a calibration of your parameters of the model, so that you will be then able to write an optimization problem, which was a problem that was solved before, and that will be used only to decide what you do next time slot. Okay. One of the characteristics of this model is that I think that I'm going to introduce it next slide. This model is an optimization model in which you will minimize the expected cost of operation for the 24 coming hours, and in the case of and that will send to the control system of your heat pump or your cogeneration system the set points to be reached. And one trick that we have used here is to say, okay, I'm going to operate with the following strategy. In fact, what I have to know is what I'm going to do in the next hour. So I'm going to set to my control system a target. You should be in this state in 1 hour. And I will calculate the state in which I have to be in 1 hour, knowing where I am and knowing my prediction. And I'm going to add an additional constraint, which is named a cyclic constraint. What I'm going to say is that the state that in which I will be in 1 hour has to be the same as the state in which I will be in 25 hours. So it means I'm imposing the system to not use the content of the storage tanks more than what is needed. So I am in a certain state today. I'm at this time now. I'm going to calculate where I have to be, what will be the level of my storage tanks in 1 hour. Okay? And the storage tanks that will be defined in 1 hour will be such that it will be the same as the one that is expected, in which I am expecting to be in 25 hours. Okay? So that I will never deplete my storage tanks more than what is needed. Okay? So I'm starting from the measurements of where I am. I'm going to make a prediction over 25 hours, and I'm going to decide what I'm doing the first hour by considering that I will look in the future for 25 hours. And I'm going to show you what is going to happen. So let's assume that I'm here. And if I'm here, and if I'm looking at for 25 hours, this is, at the time where I'm here, the prediction of my operation. So I know that in 2 or 3 hours, I'm going to start my cogeneration unit to this level. And then afterwards, I'm going to operate to a higher level for 3 or 4 hours, and then I will stop. And a priori, I will be satisfied for the whole day. This is the vision that I have today. So I'm defining, I know that I will not start my cogeneration now, and I will verify that I can do it with my storage tanks. Then I'm going to the next hour, and what you can see is that the next hour, I have now the prediction that I will not need to start my cogeneration unit. Okay? And this is explained because a priori it seems that I will not perturbate too much the temperature inside my building, so I will be able to satisfy my comfort. And I'm going just to empty the storage tanks because it seems that I do not need the heat to add heat in the storage tank. But then I go to the next hour, and then it seems that the next hour now, well, the estimations is finally telling me that I will have to start. Okay? And that's mainly because what is happening inside the building is not well predicted. So there is an error between what I'm predicting and what I'm really doing. And when I'm here, I'm just looking at what is the content of the real content of the storage tanks. And if my prediction was wrong, then I can now still correct. And then this is what is going to happen then just now. But now you can see that at this time, I know that I have to start. Okay? And then I'm going to start, and I can continue like this. And I'm going to finally, so you can see that this is what I have finally done. So I'm started to 75%, and then progressively have stopped the unit in reality. Okay, which was different from what was predicted. And it seems that here the system has tried to push the system to the limit because the temperature here has been lower than the set point. Okay, so the people have been cooled, so that's what is happening here now. Okay, so it seems that in order to limit the cost of the system has decided to stop a little bit too early. Okay, but nevertheless, so what you have seen is that I have defined a strategy of operation. Okay, and for example, here you can see that the system is going to react and has finally filled the tank and then sent the heat to the building. Okay, so this is an approach which is quite interesting, because it means that now, instead of having a system that is operated by knowing perfectly what is going to happen, I have a system that is looking at where I am and what I have to do. Okay, and this is what finally he decides. And the black one is what is really done. And you can see that it's different from what was a priori predicted. In order to be able to do this, we have to adapt the optimal predictive control model that we were using in the design phase. And what were the adaptations? The first one was to add a penalty if the temperature is going below the set point. Otherwise, as the system is trying to operate with the minimum cost, of course, the cheapest way of satisfying the heat load would be to let the temperature go down. Okay, no heat, no cost. Right? So it means that although when we have a perfect prediction, we can say, okay, this is a set point. In this case, we have to add a penalty to be sure that we will not be perturbative. Another dimension that we had also to introduce was the differentiation between the cost of electricity for import and export, because this cost was also quite can have a big influence on the way we are going to consume operate the system. Another dimension that was important was to look at the startup and shutdown procedures. So, and these are the situation we have calculated here. So the system is piloted by an integer variable that says that I'm going to start at time t, and in this case, the operation, the heat that will be delivered will be between the min and the max. Okay. But I have to add to this the fact that I have to decide when I'm going to start or to stop. And if I'm starting, I'm going to have an energy consumption. So what does it mean? It means that if the unit is shut down, it cools down. Okay, so the mass of the unit is going to reduce its temperature. Which means that when I will start again the unit, the first part of the energy that will be spent will be to heat the equipment. Okay? And this corresponds to a certain energy consumption that has to be accounted. So, and this is what is done here by defining a variable that is going to tell me, okay, I'm in the startup phase, and in this case, I will have to take part of the energy for my own usage. In addition to this, you can also add nonlinear constraints to the to take into account the part load efficiency. It's not a nonlinear; it's a linear constraint, which is taking into account the part load efficiency that is linearized. Okay. But then you have a system that can adapt to what is happening. So, for example, here you have two different type of operations. in the blue case, the cost of electricity is constant. So there is no differentiation of the cost during the day or the night. While in the red case, the cost is different from day to night. And what you can see is that the system is going to behave very differently. Okay? Something which is also interesting is that the system is always trying to trigger the temperature of comfort. The lower temperature is never reached, so it means that you have enough inertia and enough quality of the building so that you never cool down below the limit set. Okay? Because mainly you have to start earlier to be sure that you will have the temperature. And what you can see here for the blue part here is that the system has decided to store electricity, to store heat in the building. Okay, so what does it mean? It means that at a certain time, and so it is for the blue case, so it's when the cost is variable. In a certain time, so you can see here, for example, that the system is going to operate. Why? Because it's interesting. You have, this is the price. So you have here a peak that is shown for attractive price to export electricity. So the system is going to operate the heat pump. Operate the cogeneration unit. Okay. And what the system is doing, I have a good price of electricity, so I'm producing a maximum. I'm filling all the tanks. Then I'm frustrated because I would like to still continue to produce electricity because I have a good price. So what the system is then deciding is I'm continuing to produce and I'm overheating the house. Okay, so it means that I'm heating the walls and I'm exploiting the inertia of the building. Okay, I know that I will pay more because I will have more losses out of the building, but it makes sense because I'm going to make profit from the price of electricity. And you can see that it is doing the same here. So you have a peak here in production, a peak in the price, which means that you go to the maximum in the cogeneration, which means that you create a peak in the room temperature. Okay, and the system is adapting. Sometimes, okay, those numbers are sometimes not very impressive. What we can see here is that there is the possibility of saving the price of a cup of coffee each day. Okay. But it makes some money at the end of the year. Okay, and it depends, of course, if you have access to the price of the electrical market or not, because this is a very big condition here. If you have variable prices of the electricity due to the fact that the market offers you good prices, then it can be interesting. The reality is that the cost will not most probably be the biggest motivation. The biggest motivation will be most probably on how we are going to appear on the market. And so, for example, this is how the system can appear. So the blue line is how much we take from the grid, okay, for our service, and this is how we do the cogeneration. So it seems that the system is going to be trying to import or export electricity on the grid, which means also that we have to try to interact in the right way with the grids. And there are different ways of interacting with the grid. One way is just using taking the opportunities of the grid, the price of electricity of the grid, or is by committing yourself to consume or produce a certain amount of electricity at a certain time of the day, or to limit the variations that you can do. Okay? And this then for the same system can lead to very different way of operating. So this is exactly the same design, but sometimes I'm in this one, for example, I was imposing a certain amplitude, so I do not allow big variations, while here I let the system no, this one I allow a big amplitude. Here I'm allowing a smaller amplitude, and by this way the system is going to react in another way. Okay? Now the question is, what is the best situation? And this is coming from the grid operators that do not know. Okay? The grid operator would be really happy if he would have to supply a constant amount of electricity. Okay? But they are not able, because they are mainly market players, they are not able to tell me what is the best situation for you. Do you prefer that I'm producing, or do you prefer that I'm consuming your electricity? And this is something which is then creating a big question. Just to show you here, so it's a big system with an engine and a heat pump of 2 megawatt and 200 cubic meters of storage tanks. Changing, so this is the price signal that I receive. So either this one, it is the night and day tariff. Here it's more with variations, with 2 peaks. And what you can see is that the system is going to really behave in a different way. Okay? In this case, it is going to use the cogeneration. In this case, it is going to use the low price during the day. It uses the heat pump. Okay? And of course, it will appear in another way in the on the grid. Okay? So something which is important here is that you can see that as the system knows that the electricity will be cheap, you can see that it has emptied all the tanks to be ready to consume the cheap electricity. So it has taken actions before, so that it guarantees that it will reach the zero, so that you will fill the tank later when you have the low price of electricity. Another dimension which is interesting there is that the people from the electrical grids and the people from the thermal side do not speak the same language. Okay. First, they do not have the same time scale. So my colleague in electricity is, so it's Paolo here, is talking about a time scale of 100 milliseconds. Okay. While here I have a building that is moving with hours. Okay? But still, the two are interacting one with the other. And so it means that when you do the predictive control, we look at one, defining what we will do during the first hour with a 25 hours prediction, okay, and a cyclic constraints. While, in fact, during the hour, to follow the strategy, I will have also to divide it into 15 minutes and 5 minutes, perhaps to react to all the stochastic operation that is occurring during the day. And something which is important there is the photovoltaics. So I'm still working on the same system here, But now I'm going to not work as with the feed-in tariff, like what is done for big installations, but with a situation where I have to try to maximize the self-consumption that I'm doing from my PV panels. Okay? So it means that I have to manage my system that is here in such a way that I will maximize the self-consumption of the solar panels that I have. Okay? And for the design, I'm going to add another dimension. What is the best size of the photovoltaic panels? Do I have to cover all my room or not? Okay? And so what we have done, it was together with Paul Stadler. So we have the system that I have already shown. We have a B-level optimization strategy where we have, on the one hand, the definition of the size of the different equipments, and on the other hand, the slave optimization, which is used for a set of typical days. The typical days have to be selected not only for the heat, the typical heat demand, but also for the radiation. So it means that we are going to define the typical days considering different criteria. So the presence of the people, the availability of the solar radiation, and the ambient temperature. Combining all these demands, then we need, in fact, more days to represent the typical operation. In this case, it was 18. And then we obtain this kind of curve of results. So on the x-axis is the amount, the covered area by the PV panels per heated area. So it means that if I'm one, I have one floor house. Okay. If I have 0.5, I have 2 floors. If I have 0.20, I have 5 floors. Okay. And we are going to plot different values. The SC is the self-consumption, so it's the amount of the electricity that is produced by the photovoltaic panel that I'm able to use on site. Okay, so it means that when I do not have a lot of solar panels, I'm here and I'm using the overall amount of electricity that I'm producing. But if I'm increasing the size of the photovoltaic panels over the year, I will have more and more electricity that cannot be consumed locally and that has to be sent to the grid. Okay? The second dimension here is the self-sufficiency. So SF is a self-sufficiency. What does it mean? It represents the amount of the, it's the ratio between the produced electricity by the photovoltaic panels and my own consumption. Okay? Of course, if I'm increasing the size of my photovoltaic panels, I will use more and more of the electricity that I'm producing. But at the same time, I will export more and more and more. Okay? So it's just a fraction of the electricity, the additional electricity that is then finally used. And what I'm going to do, I'm going to make a special calculation. On the one hand, I'm going to calculate what is the, I'm going to calculate 4 different cases. The first one is what is the best profit? So how many square meters do I have to buy at the price of the market to make the best profit of my investment? And I would like to know what are the square meters that I need. Okay. The second one, the second element here is what is the annual energy bill? So the green people, so the one that says, okay, I'm producing the energy that I'm consuming over the year. Okay, so what we can see, this is this point here. In this system, in fact, to be self-sufficient, you have to ask the grid to take care of about 60% of your production. And only 40 can really be used directly by you. Okay? And then we have made a strange calculation. We have calculated what is the size of the battery that is needed in order to receive this 60% back to be self-sufficient. So this 60% have to be sent to the grid. It will be considered to be stored in a very big battery, so that we will be able to reuse it after when we need it. Okay? And the two other points, the 2 and the 3, are considering the efficiency of the battery. Okay? So this is 80% and this is 55% round trip efficiency. Okay? So it means, of course, that if I have a certain efficiency in the battery, I will need more photovoltaic panels. Okay? And it will be even worse if I have a lower round trip efficiency. Okay? So let's look at the results. First result is for a single family house with a heat pump. You calculate here the size of the heat pump, how many cubic meter of hot water tank you need, what is the size of the battery, and how much PV panel do you need in order to be self-sufficient yearly. And you need, so you have a two-level building, which makes 80 square meter of PV panel to be apparently green. Okay, but it's apparently because you still, if you look at the value here, 60% of your production has to be taken care of by the electrical grid, which means that you have, if you would like to be really self-sufficient, you would have to buy a battery of 4 million Swiss euro. Okay, right? And it will be even worse if you consider the efficiency of the battery, okay, or the long-term storage. So what does it mean? It means that the batteries are not the right way of storing electricity for the long term, right? And just to give you a flavor, so you need 8 megawatt hour of battery, and this is a battery of 0.5 megawatt hour. Okay, so what does it mean? It means that you need a second house just to store the electricity that you need if you want to do it with a battery. Okay, by chance, so there are dams everywhere that can take care of this. But this is, I think, interesting to see. Second situation, and the third case, and then the fourth case is what is the best if I want to make the maximum profit of my investment. And then the answer is buy 4 square meters of PV panel. Okay, costs nothing. In this case, you can buy it in Micro. But this would be the one that is giving you the best return, because you are using everything that you produce. And in fact, if I'm looking at what is happening here, it's the first square meters. In fact, I can consume all what I'm producing, and these are the ones that have the highest profitability. Okay, so it means that, and this is also the one that I would have to recommend if I would be a perfect economical person, driven by economics. Okay, and following the rules of the state. So it's not, this way is not the way to promote the penetration of renewable energy. On the other hand, so the redox flow battery will be quite small. What is behind this is the calculation of the strategies. So it means that you can see that the strategy, the system will try to make the best use of the production. Okay, to decide when to operate the different systems. I'm just going to jump to, to this curve, just to show you what is the influence of the predictive control in the system. So the red curves here, again, is the self-consumption and the self-sufficiency without predictive control. Okay, and the black one is the same situation with the predictive control. So what you can see is that if I'm taking this point for a given area of PV panels, I can go from this situation to this one. Okay? So it means that I can increase the self-sufficiency or the especially the self-consumption by 68% by just having a smart system that is operating the heat pump together with knowing when the sun is shining. Okay, and I think it's quite impressive because you can see that you go from 20% of self-consumption to 40%. So it's quite nice as a result. Okay, and the last things that I wanted to show you is this one. So why do we have to avoid using electrical heaters even if the electricity is produced by renewable energy sources? Okay, this is the situation with a heat pump. So the sun does not allow me to. So you see, it's around 0.5. Huh? While if I'm doing the same building, but with direct heating, direct electrical heaters, so you need, instead of 0.6, let's say, you need 1.2. So you have to buy twice the size, okay, to reach the same level as this one. Okay. So it's at the end, it's a good message as well. So you do not have to use direct electrical heaters. Yeah.
If it was possible for interesting, use the size of your inverter and compared to PV panel power, the power of PV panels.
See it again?
If you install a maximum power DC power of your panels, for example, 1 kilowatts, and you buy inverter of 800 watts.
No, this we have not investigated. So we always buy the inverter needed. Okay. Because we assume that everything is set on the AC. But this is an interesting message. Of course, we can do the same for the cogeneration and for the combination of heat pump and cogeneration. And in this case, of course, we receive other results because the cogeneration is in competition with the production of electricity. Okay? And by this way, the optimal size of the system is less attractive, I would say, because we have to find other justification for using it. Okay. Something that can also be done with the system is to try to, and this is also things that we are trying to study, is to make a prediction of what will be the electricity consumption of my system. So how I will appear on the grid. And one possibility that we are investigating is to say, okay, if I'm able to tell the grid, this will be my energy consumption, my electricity consumption, then what I can ask my controller is to do what he has declared that he will be able to do. It means that at a certain time of the day, we are going to say, okay, for the next 24 hours, this will be my electricity consumption on the grid. And we are going to use the optimal predictive control system in order to realize what we have declared. So it means that if the people change their mind, or if they are not at home, or if the sun is changing his mind, we will try to nevertheless appear the same. And this would be really interesting because then we are predictable for the grid operator, which is for him very interesting. And this is what we show here as well, is the possibility of either operating between bounds or taking, realizing what we have to and this brings me to the conclusion, and then I will make a break. So, two major conclusions. On the one hand, we have made the design taking into account the fact that we have a predictive controller system. Okay? Which is typically what is not done. So typically the people buy an equipment and then try to put a box on it. Here we use the design, we make the design knowing that we have a control system. Which introduces a next challenge, because the size of the equipment will be just the one that is needed, not too big storage tanks, for example. So it means more efficient, but needing a smart control system, much smarter control system, because there is much less flexibility in the design. Okay, but then when we adopt this approach, then we will be able to be very efficient. And I have shown with the example of the PV panel that we were able to absorb much more renewable energy that is locally produced. And the last dimension is what we have learned from the discussion with the people from electrical engineering, is that we have to change, we have to adopt a common vocabulary. Okay? Which is not so easy. So V. Most of us would consider that V is volume. Okay? In electrical engineering is voltage. Q in thermal engineering is heat load. Okay? In electrical engineering is reactive power. P in our case is pressure. Okay? In their case is power. Okay? And it's not a joke, because we have to learn to discuss one with the other. They are not using the same time scales, and they are not using the same vocabulary. Okay? And if we look now at in the scientific communities, a lot of people that do this kind of design in the mechanical engineering journals, and there are others that are using different tools and methods in the electrical engineering journals. Okay? And typically they are not looking one to the other side. I must admit that I was in this case before starting working with my colleague. And it's interesting because then you miss opportunities. So the first time I have received money for doing this research was by the people from the electrical from an electrical company, and I have heard them because I have said that I'm going to maintain the quality of the grid. They say, our grid has a high quality. Okay, but my major purpose was to say, okay, you will have less variations, because I will be able to manage the variations by my system. Okay?